Hello. So, as we discussed last time, linear Kalman filter, and we derived the equations and see the some Python simulation as well. How we can use Kalman filter for state estimation. So, Kalman filter, let's revise it. So, Kalman filter has two stages, as you see. First step is the motion using motion model uh, to predict the state. So, in that it means that you have let me open this one. So it means that you predict your state from time t, let's say time t minus 1 to time t. If your state at time t minus 1 is, let's say, xt minus 1, like this, you predict it in time using motion model, and you get your state at time t, which in some time we express like x hat minus just dash. So this shows that this is the predicted state, this one. And the second step is measurement model. Using measurement model, we update our predicted state. So let me draw the timeline here. So you have time steps here, t minus 1, t plus 1, like this. So here you have the already known state at time t minus 1. So you predict it to next time step at time t, and let me call it hat minus a hat dash something. So this shows the predicted state as we mentioned. So this step using motion model as we said. Now what happens that after the motion model, if the sensor measurement arrives, sensor measurement arrives at time t, so we can incorporate that sensor measurement into the to update our state. So we'll see the equation later, but after the incorporation of the state measurement model in your state predicted state, your state will be updated at time step t. And next the same process will go on, that you have this state at time t, you use the motion model to predict it at time t plus 1, and once you get the sensor measurement, let's say time t plus 1, and then you update your state at time t plus 1 using sensor measurements, like this. So this process goes on. So the current filter use 5 equations. Let me summarize it below. So use these 5 equations for state uh, prediction and state update. So these two equations are the state prediction equations, state prediction. So in which you see that you have two equations. One is the two, one, two. So one is state prediction using the state system matrix A, control matrix B, and control inputs U. So you have the previous state, you can and the input control input, the previous state, the state, let's call it state. So if you have these two inputs, you can update your you can predict your state to x hat k minus minus, for example, we calculate minus predicted state using these system model and control model. This equation number 2 gives you the formula to update your. sorry, not update. I should use the correct word. To predict your state error covariance. So in Kalman filter, we not only predict the state, but also we produce this state error covariance matrix, which will show the uncertainty in your predictions. So this is the formula for equation number 2. So what are the inputs to this formula? System model noise matrix, system noise matrix, then your system model and previous uh, state covariance matrix, and you will update, you predict your uh, state error covariance matrix. Let's see the step number 2. So once you predict your state and get the predicted error covariance matrix, and when you get the measurement from the sensor for your state, you can update your states. So in the update of the states, there are three equations. Let me write first here. This is the state update step. So in state update step, you use three equations. That we got equation number 3, then 4, and then 5. These 5 equations are the set of Kalman filter. So in equation number 3, you calculate Kalman gain first. So and then equation 4, update your state prediction, which you have state prediction already you from this step, and you add in that predicted state this term. So what is this term? So this term is first you calculate the difference between the sensor measurement and the state prediction. So the C X is your system model, sorry, measurement model. So what is measurement model? It means that the sensor measurement model means that, let me write fully, sensor measurement model. It means that how your states are uh, related to the sensor output. So using this formula or this relationship, functional relationship between the state and the sensor output, you can predict your sensor measurements. So this is the this term C X hat K is a predicted state. Sorry, predicted measurement. Predicted measurement. Let me write the in full, right? Predicted measurement using predicted state and so this matrix. This matrix is called measurement matrix. This one, C, measurement matrix. So this is your state measurement prediction. So you take the difference between the actual sensor measurement minus the predicted sensor measurement and multiply with the Kalman gain. So this term is very important. Uh, Kalman gain. And you add this term, this multiply of Kalman gain with the difference between the sensor measurement and the predictor measurement. You add this term with your state prediction, and you update your state. And once you update your state, in question number 5, you also update your state error covariance matrix. So this 5 question will give you the full state estimation using prediction and update measurement update steps. So here is the summary of I mean in the visual Visually you can see these two equations and three equations. So this is the time prediction using motion model, and then we have, once we get the sensor measurement, we get uh, update your state, and then this loop continues as long as your sensor measurement is coming and your motion model is updating. So there are good video tutorials. You can watch these video tutorials related to Kalman filter, and you will have more insight. So this linear Kalman filter is good or optimal when both the sensor model and measurement model are linear. So, but if any of these models, sensor motion model or measurement model, has a nonlinearity, then linear Kalman filter does not uh, produce the optimal solution. So, how we can incorporate the nonlinear models into the equations of the Kalman filter? This is the topic of next. Okay, let's start the Kalman filter for nonlinear system, which is called the extended Kalman filter. There's good tutorial here. I think you can see it later also. So why we use why we need to modify linear Kalman filter? Because in nature most of the systems are not linear. Even if you see the very simple the system, like let's say the relationship between the voltage and current in a simple resistor. So usually we take it linear, but it's a linear under a certain portion, right? Like this portion. But after that, the starts behaving non-linearly after some high voltage and high currents. So this Ohm's law, which show the relationship between the current and voltage, is only applicable in this linear region. So another example is let's say our robot moves, or it takes a sharp turns on some road or some path. So then it also shows a nonlinear behavior. So in that case, if you want to need the estimate the state of that vehicle or that robot, state means that let's say we want to calculate the position, the velocity, or velocity, for example, then we cannot use the extent linear Kalman filter for nonlinear system. So EKF was the just extension of the linear Kalman filter. People realize this problem, that it is not always linear filter is not always optimal. So then they have to think about the how we can use this similar model for the Kalman filter equations for EKF for nonlinear system. So, for example, the the motion model of in general of any system can be given like the function of the state, function of control inputs, and motion models or process noise. So in general, it can be a nonlinear. But if we in previously in Kalman filter we write this expression as a linear function, like for example xk, we write it like f xk minus 1 xk minus 1 plus, let's say, bu uk minus 1 plus some noise. So this is the linear version, but this is the nonlinear version. Similarly, the sensor models or sensor measurement models, in general, they can be written as a function of the the predicted state and some measurement noise uh, in in general. But the previously we write this model as a linear function, using a matrix H. Matrix H is a measurement model, capital H, big H, and then multiply with the state, predict state, and add some noise. So this is a linear version, but this is the nonlinear version in general, where the the process noise or model motion model noise and the measurement noise or sensor noise can be considered as um, normally distributed or Gaussian with zero mean and with some variance or covariance. So these are the ingredients of EKF. So let's see in detail how we can incorporate these the five equations of the linear Kalman filter to incorporate nonlinearities of the system. Mathematical model, I mean the nonlinearity of the motion model or nonlinearity of the measurement model or both. So for that, first we need the concept of the linearization of a nonlinear model. This is a mathematical tool like the first order Taylor series expression to linearize a nonlinear function. So we can make use of this nice mathematical tool to extend our linear Kalman filter equations to nonlinear systems. So for example, in general, if we have a function f of x, we can linearize this at a point A. So let's see, like this. So let's say we have this function which is nonlinear. So we can linearize it at let's say at point A, and we take a derivative at this point A, and then we can predict this at next time x. So we can take the derivative at this point, and then we multiply with the difference between x and a, this term, and that will give us the next point on this line. So there is a little error if you see here, depending on the nonlinearity. So sorry, let me save it. So there maybe you can observe a little difference between this point and this point, right? Let me give different color. That's this point, right? So this is the okay. This is still very less error. As you reduce this step, as you reduce this step, this error also reduces. So this way you can say the stepwise linearization of your nonlinear function. So Taylor series gives this nice approximation of a nonlinear system. And then this is the linearized model, first order, if you ignore the higher order terms. So we can linearize, it means that we can linearize motion model and measurement model if they are nonlinear using this Taylor series expansion, first order Taylor series expansion. So how it will look like? This is our nonlinear function. If we linearize it at the some state and also at some control input, so we can get this linearized model. So in the first time we have this calculate this function at some time some x hat and u, and then add this partial derivatives derivative terms, multiply with the difference between this the predicted state and the previous state, and similarly we calculate incorporate this noise term derivative. So this way we can get this linearized motion model using first order Taylor series. and we can use this to predict our um, state. Similarly, if we look at the linearized model of the measurement model, then we can use first order Taylor series again, uh, calculate the function h of x at predicted state, and add these partial derivatives with respect to x predicted and with respect to measurement noise, and we get this H matrix and M matrix. So these four matrices F, let's say we call this in this case L, which is a partial derivative with respect to the process noise. F is a partial derivative with respect to the state, updated state, and H is a partial derivative with matrix with respect to the predicted state, and M is a partial derivative matrix with respect to the measurement noise. So these four matrices, if we calculate these four measurements at appropriate um, timing, appropriate timing means that at the let's say F matrix and L matrix will be calculated in the prediction step, and the H matrix and M matrix will be calculated in the measurement update step. So then we can incorporate the five equations of the linear Kalman filter uh, to make it like extended Kalman filter, and we can estimate the state of a nonlinear system as well. So let's have a deeper look at these four matrices, which we call it F, L, H, and M in this case, because these are the core to EKF. To calculate these four matrices is a core to EKF. So let's have a deeper look at how we can calculate these four matrices. So these matrices in mathematical terms, they are called the Jacobian matrices of the system. So what is Jacobian matrix? So Jacobian matrix is simply the matrix of the partial derivatives of a vector valued function. So let's have a look at an example. For example, we have vector value. We have vector x, which has two components, x1, x2, two state components, and we have vector valued function f of x, which has let's say these two functions x1 plus x2 and x1 square. So how we can calculate the partial derivative, or how we can calculate the Jacobian of this matrix, vector valued function. So to calculate this, we just uh, um use this mathematical notations, like in the first row. So because we have uh, this vector state vector is 2 by 1, and we have the function, we have two functions as well. So our Jacobian matrix will be 2 by 2 in this case. If we have um, more number of let's say if we have more number of state vectors, state variables, let's say, let me give more examples so it's easy to understand. If we have, let's say, three functions, right? So not three, let's say case number one. Case number one, your state vector consists of three state variables, and your function x, f of x has two functions, f1 and f2. Then your Jacobian matrix will be, so let me write down full. So Jacobian matrix will be like this. So in the first, you calculate the partial derivative of function 1 with respect to x1, then 1 with respect to second state variable, and function 1 with respect to third state variable. And in the second row, you take the second function and take the partial derivative with respect to the first function, and second function with respect to second variable, and second function with respect to third variable. So in this case, what is the dimension, right? So 2 rows and 3 columns. So this is your Jacobian matrix dimension. The second case, we have this space here. Try. Okay, we have the second case. Let's say we have case number 2. We have a state vector with 2 variables, and we have a functional function f of x with 3 functions. Then what will be the Jacobian matrix in this case, right? So same way you follow the same convention. You take the first function, calculate the partial derivative with respect to first state vector, state variable. Take the first function, calculate partial derivative with respect to second state variable. In this case, you have only 2 state variables, so you just finish here. In the second row, you take the second variable, second function, calculate partial derivative with respect to the first function, take the second variable function, and calculate the partial derivative with respect to the second function. Same way, you take the third function and calculate partial derivatives with respect to first and second state variable. So, sorry, 2. So in this case, if you look at your state matrix dimension, it will be 3 rows and 2 columns. So this is how properly you can find the dimension of your Jacobian matrix before. I mean, if you calculate wrongly, so of course it will affect your calculations, and your state estimation will not be the correct. So you must pay attention to this calculation, right? Calculation of Jacobian matrix and their dimensions properly. So once we have uh, calculated these partial derivatives, let's say partial derivative f, partial derivative uh, in this example, in this notation we call b or l, this same thing, l, partial derivative of the control variables, and h, h matrix, and also if we need m matrix also, so m matrix. So once we calculated all these partial derivatives properly, we can plug in these partial derivatives in the prediction step and in the correction step or measurement update step. So let me explain a little bit these 5 equations again in the context of EKF. So let me explain these equations in EKF. So we call it EKF in short. So again in EKF, the 5 equations as in the linear Kalman filter, 2 equations for the state prediction, and then other equations for the state update. So let we explore one by one. Equation number 1, equation number 2. So equation number 1, you take the nonlinear function as it is and input your state and input your control inputs, control, and then your nonlinear function will I mean the uh, propagate these your state using this input, and it will show you the predicted state. So you have 2 notation. You can write like this, or it is same thing that you write it in the previous way, like x hat minus. So this is your predicted state at time K. And same way as you did in the linear Kalman filter, you will predict your state error covariance matrix using equation number 2. So in equation number 2, what are your inputs? Of course, your previous covariance matrix and your control inputs and your noise motion model noise matrix or process noise matrix. So along with it, here we see the matrix F. So this big F and small f, they are different. So small f is a nonlinear function, but big F is a partial derivative. So partial derivative matrix, you can say Jacobian matrix of motion model. This is F. So you calculate Jacobian matrix uh, of motion model at the predicted state, and you calculate your this one. You can write this in the previous notation, like EK minus predicted error covariance matrix. So next, when once we get the sensor measurements, we apply this correction step, or you can say the measurement update step. Update step. So in update step, again the core equations are only three. This equation number 3, as in the same as the linear Kalman filter, equation number 4, state update equation, and equation number 5, error covariance matrix update. In equation number 3, first we calculate the Kalman gain. So you calculate Kalman gain using this S matrix. So what is S matrix? It is the predicted covariance matrix here you have, and the Jacobian matrix, measurement Jacobian matrix here, Jacobian matrix of measurement model, measurement model H, big H. So big H is a Jacobian matrix, small h is a nonlinear measurement model, and you add this sensor noise matrix as well, and you calculate this term S. So this term S will be used to calculate the Kalman gain. Once you have the Kalman gain, same way you first to make the error between the actual sensor measurement Z of k in this case, actual sensor measurements, and minus the measurement prediction. So H matrix is here, is the, I mean this term H of x k hat is your nonlinear measurement model, it can be linear, it can be nonlinear, so that's why just I take this measurement model and take the difference between the actual sensor measurements and the predicted sensor measurement, and then multiply with Kalman gain and add in the predicted state, and then this way you update your state estimate. Once you have updated your state estimate, you also update your error covariance matrix in equation number 5. So this way you recursively update your first predict, then update, predict, update your state estimation using these 5 equations for nonlinear systems as well. So here the summary of the EKF algorithm. So same equation, we have the measurement, nonlinear measurement model, nonlinear system models, and then you apply these the prediction steps, state prediction step, and also you apply this state update steps by calculating uh, the Kubin matrices at appropriate instant of time with appropriate vectors. Right. So this is the theoretical part of EKF we did. So next we will do some example how we can use this EKF equation, the EKF model, for estimating a state of a, let's say, differential drive mobile robot. Okay, next we see the sensor model or observation model, how we can incorporate the sensor measurements in the state prediction, which is produced by the system model. So observation model, what is observation model first of all? So observation model will give you the predicted state. If you, for example, if you know the state, predicted state, for example, this one, okay. So the the h function will tell you what is your predicted state at time. Let's say this k minus 1 and at time k. So if you look at the timeline, so it will be something like that. So your time k like this, let's say k minus 1, k plus 1. Then you have the, let's say you start from here at time k minus 1. You have your state available at time t k plus 1. You use the, and not only state, but you also know the initial covariance matrix at that time. Then you predict your state using motion model, let's say f of whatever, f nonlinear function, and you get the predicted state at time k. And also, of course, your covariance matrix at time k minus 1. I have to give those notations. So then at time k, you get your measurement at time k. But you can also predict your measurements using your motion model. Uh, this one, using a motion model here, zk at minus. So using this predicted state x at k k minus 1. So basically you have this is not k. So you have this predicted state, and you can use this predicted state to calculate your predicted measurement. Right. So then you take the difference between these two, predicted state and the actual sensor measurements, and multiply with the Kalman gain at time k, and then add this term in the previous, not previous, the predicted the state, this one, and you update your state at time k like this. This is your main equation of the Kalman filter algorithm, that using the difference between predicted state and the actual sensor measurement, predicted measurement and the actual sensor measurement, multiplying with Kalman gain, adding with the predicted state, you update your state. This is main equation of the Kalman filter type of the algorithm. And then the process repeats that once you update your state, and also you update your covariance matrix at time k using some equation we'll see in EKF. Then you repeat this process for the next time instant, and when you get the sensor measurements, you take the difference between the actual sensor measurement and the predicted sensor measurements, and then update your status. So this process repeats until the process continues. So we have to linearize the measurement model or sensor model if our the function h is not a linear. If it is not linear, we have to linearize it. If it is already linear like this, what do you mean of linear sensor model? Means that let's say you have your mobile robot, you have a sensor, GPS on top of it. You also have other sensor, a compass on top of it. So GPS will give you the position at every instant of time. Let's say every 1 second, and your magnetic compass will also give you the heading angle with respect to the north. So you get the x, y, and angle at every instant of time. It means that your measurements from your system are x position, y position, and angle. So because your state vector is also what? Your state vector is also x position, y position, and angle. It means that you are directly observing or directly measuring your state vector from your the sensor. So in this case, your H matrix will be the linear matrix already. So you can write your H matrix in this way. That first, let me note it, y1, y2, y3. These are your three measurements. The first measurement is your x position, second measurement is your y position, and third measurement is your angle. So H matrix will be just will take this form, linear form, 1 1 on diagonal, and after terminal to 0. But what if you have a sensor which is not directly giving you your state variable, which is not directly measuring your state variable? For example, you have a robot which has a sensor, let's say lidar sensor. You have a robot over here, and then this robot is see some object in the space and calculate the position and angle, that will called theta, position and angle with respect to that object. So that object, that's the object in the space, in the environment, is at known location, known global position or location. It will be that if you observe an object at a known location, known global position in a global map, for example, so then you can calculate what will be the the position of my robot. Let's say this is your global frame xg yg, and this is your let's say local frame, and local frame you observe this target at non location. So what mean that you observe this target, you are getting two measurements. One is the distance to the object, non-object, and one is the angle to the non-object. So what will be that? So so in general we can say that let's say the robot is let's call it x and y, because we're considering two D case. So there's no y here. So 2D case. So let me say for convenience that the robot frame and the global frame are coincident. It means that the global frame is also here. So you're getting the range to the object, and you're getting the angle to the object. So how you can so these are your measurements from the sensor, right? So how you can correlate, or how you can find the relationship between the sensor observation or sensor measurements to the state of the your robot. So in this case, R range will be, if this is 0 0, let's say 0 0, it can be in another case that in general this can be non-zero, but let's say it is 0 0. Then what will be the range? Range will be the x square plus y square under root. In general, if it is non-zero, let's say we have the robot location at not 0 0. Let's say we have robot location at let's say xr or yr. This is robot location in the global frame, and global frame is somewhere located here 0 0. So in that case, your range formula will be modified a little bit. So range formula will be modified at x minus xr square xr square plus y minus yr square and under root. So in this case, if it is global coordinate frame and local coordinate frame of robot are not located on the same origin, but they have some uh, displacement vector like this. The second measurement which we are getting from this sensor, let's say lidar sensor or radar sensor, is the angle to the object at known location. So that angle is this theta. Okay, so this theta is simply tan of y coordinate over x coordinate. So again, if uh, your robot is not coincident with the global frame, so this y coordinate will change by y minus yr, and x coordinate will change by x minus xr. So in general, this is valid. So your robot can be located at any location at x, r, y, r, and then your the angle to the object, angle measurement, to object at known location, and this is the range measurement to the object at the known location. So these are your two sensor measurements, range and angle to the object at known location in the global frame. So it means that you can write, let me write down here in a simple way, R as x minus xr square plus y minus yr square under root, and second equation angle tan inverse y minus yr x minus x. Let's write question number one. Question. So these are your um, sensor measurement model. These two equations are your sensor measurement model. Let me write out here. So sensor measurement model. Why? Why we call it like this? Because your sensor measurements are range and angle, and these two sensor measurements are showing the relationship between your state, which is a state. Your state is x, y, and angle. X, y, and gamma angle. Let's say. So they will give you the relationship between your state and the sensor measurement. So it means that if you can write these two equations in let's say r and theta, like something like that. Not like this. Uh, so you can write these equation r and theta in a like this with some noise added. This is your sensor model in general. So the function h here, you see it is nonlinear. Okay, so how to linearize it so that we can incorporate this in the EKF. H function to get h. So h, what is that? Jacobian matrix. We call it measurement Jacobian matrix. So same way, you can in this case you have two functions, h1, h2, and you have your three states. So your state vector is 3 by 1, and your functions are you have two measurements. So the Jacobian matrix will be what? Can you guess? 3 rows, 2 columns. This will be the size of your Jacobian matrix um, if you have two functions. So you can calculate your measurement Jacobian matrix in the same way that you take the first function, take the partial derivative with respect to the first state variable, then take the first function, partial derivative with respect to the second variable, state variable, similarly first function, partial derivative with third state variable. That will be first row. Similarly, take the second function, calculate partial derivative with respect to the first state variable, second function, and second variable, and second function, and third variable. Right? So this will be your calculation of your. So you can verify step by step that what will be your each element like this, from let me call it model three, question number three. If your model is already linear, it will be h will be like this. If it is non-linear, h will be like this. Partial derivatives. So once you calculate the measurement Jacobian matrix, you already calculated the system Jacobian matrix, input vector Jacobian matrix, and also now you calculate the measurement Jacobian matrix. Now you are ready to uh, apply your EKF equations to this example, which is a example of a ground mobile robot, differential drive robot, using the system model and observation model. So let's for example, you initialize your robot with a state. Let's say state initially at 00, meaning that your global frame and your local frame are on the same x robot, y robot, in the same direction as the x global, y global. In this case, your position is 0 and orientation or angle is also 0. But after some, in general, it may not be 0, as I said. It can be, your robot can be at some position x0, y0 initially, some angle. I mean, in general, it can be like your initial state can be like this, xk minus 1. Let me write it like this. So this notation and this notation are same. Some books write this notation like xk minus 1 given k minus 1, that is that time k minus 1, and then they write it like this. The notation meaning the same, right? That you have your state vector at time k minus 1, and now you can use this initial state to propagate through the your motion model. So let's say initial state in general can be x0, y0, gamma 0, or it can be, let's say, if you initialize 00, it can be this, it can be 0. And your initial noise vector, you can assume some random numbers. In this case, let's say it is 00, but you can take some small values in your motion model, in your motion model as noise vector. And initialize your state covariance matrix. So what is that? So initially you have you also, so this notation and this notation have the same meaning, that k minus 1 plus. So for initializing, we will initialize with some small numbers, on the diagonal, and after elements will be 0. So we need to initialize our Kalman filter algorithm using this initial state vector and initial state error covariance matrix. And then, as usual, we start the prediction step, then update step, then prediction step, update step at every instant of time. When your sensor measurements arrive, you can update your prediction. In between the sensor measurements arrival, you predict your state using the motion model. So next, after initialization, you go to the second step, which is prediction, a state prediction step. So you use your Jacobian matrix A calculated at the current as state estimate. Also, you use the input Jacobian matrix B and add some process noise. So in this case, we predicted our state and state from time step k minus 1 to time k, and also we predict our state covariance matrix using the Jacobian matrix calculated uh, as f. Sometimes you say the f, sometimes you call a. It is the same thing. Notation are different, but it is Jacobian matrix of the system model. And also you add this process noise matrix. This process noise matrix can be the constant some small matrix with a small numbers on the diagonal. but it has some mathematical form, but we're not considering it here. Just for the sake of simplicity, we take it as diagonal matrix with some small number. Okay, so here describe that it's nice covariance matrix is the covariance matrix which can have the variances, nice variances on the diagonal and off diagonal elements of the covariance values or correlation values. So you predict your covariance matrix, state covariance matrix using this formula, and if we plug in some numbers uh, which we can, because this initial state covariance matrix, this is the Jacobian matrix, system Jacobian matrix, transpose of system Jacobian matrix, and then this is the process noise matrix. And our prediction step ends here, right? And next we go to the measurement update step. In measurement update step, uh, the first thing is that we have to calculate the difference between the actual sensor measurement and predicted sensor measurement. Predicted sensor measurements will come from the sensor model, which can be linear or which can be nonlinear. So this term, which we take the difference, it's just given some name, that innovation, innovation or measurement residue. So if you see in some books or some tutorials, they say the innovation vector. So don't be afraid. So innovation vector just the difference between the actual sensor measurements and predicted sensor measurements. So this vector will be has the same dimension as your number of measurements. If you have two measurements, it will be 2 by 1. If you have three measurements, it will be 3 by 1. So this residue, measurement residue, is then multiplied with the uh, Kalman gain, right? So let me show that equation first. So it will this measurement residue will be multiplied with the Kalman gain k and added in the previous the state. I'm pre-stating that the predicted state, and we get the updated state. This notation is same as we write it like k hat plus, right? Sometimes we write it like this. Sometimes we write k given k. So it is same thing. Notations in different books use different notation. Some use this notation, some prefer this notation, but the meaning is same. And after that, we calculate the state covariance matrix. So these equations are already given the algorithm of your EKF. So in that you have your Kalman gain already calculated, Jacobian of your measurement Jacobian of M measurement model, and this is your um, the state error covariance matrix predicted. I mean this write it in other notation. Write it like this. This one state error covariance matrix predicted state error covariance matrix, and you get this updated covariance matrix plus, right? Okay, one some this like this where is that? This equation has two actually forms. One is this one, which is simplest, that 1 minus kh multiplied with the p. But in some books, it is more. Let me go to the previous slides. it has some one more term. For example, here, um, no, this Kalman gain. So Kalman gain has this form where we incorporate this S matrix. So S matrix is what? S matrix is the matrix of the innovation, what we call the measurement reservoir innovation vector, covariance of the innovation vector, covariance of the measurement residue, covariance matrix of the. So we incorporate this in over here. So basically, you have three equations: this one, and this one in update sensor update equation, and you have two equations, this one and this one, in your prediction step. So here, during this example, you calculate this measurement residue or innovation vector, and then you also calculate your where is that? This one, innovation covariance matrix, which is nothing but the covariance matrix of your measurement measurement residual vector corresponding to your innovation vector, right? You got the measurement residual vector. So use this covariance matrix in your Kalman gain calculation. For example, here, right? You have okay, you have this one, you have this one, and you plug in your Kalman gain equation, calculate Kalman gain and this, and then you finally you calculate your update your state using this fourth equation, and then you calculate your update your state error covariance matrix using this fifth equation. So these are the steps in EKF. Um, so I gave you the all the steps, demonstrated with some numerical example as well. How to initialize, how to calculate the Jacobian matrices at every time instant, and then how to predict your state, how to update your state using EKF algorithm. At the end, I gave some this Python code. So for example, initialize 0, 0, a state vector, and then you can update your, let's see, you get the sensor measurements at time 5 time steps. So first 1, 2, 3, 4, 5. So these are the measurements of your sensor. You can incorporate these measurements in your prediction uh, state, and then you update your state. Right. So you can see that how your robot will move uh, using this state model, and if you also give some vector input vector, let's say velocity is 4.5 meter per second, and your angular rate is let's say radian, 0 to 0, omega is let's say 0. It means that we are not um, not rotating, but just uh, moving in a forward direction. So even though you are moving in the only x direction, but still you see that there is some position changes in the y direction as well. This is only due to the sensor noise. But you can produce using this example as a baseline for your um, 2D state estimation, or even you, you can extend it to 3D state estimation. So there are a lot of examples available on in Python, MATLAB, how to use EKF and Kalman filter or EKF for the state estimation in 2 dimension and 3 dimension. But the thing is that the codes are available, but most of the students, they don't understand the mathematics behind it and the steps involved in the derivation and also in the application of these mathematics to the coding. So in this tutorial, I gave you a small uh, in-depth in-depth like mathematical treatment of this subject. So please go through my the lecture slides. I will upload it on your MS Team, and also you can watch this my lecture tutorial, and also you can watch other tutorials on YouTube. A lot of, but the thing is that you understand fully all the mathematics and the steps involved. Okay. So thank you very much.